Hey everyone, so today we're going to learn about definite integrals as Riemann sums and also Riemann sums as definite integrals. So let's take a look first at sigma notation. This should be something you remember from either algebra or pre-calc possibly. So in a general sense, sigma from 1 to n, if you guys kind of remember, this is a Riemann sum and you're basically taking the sum of n number of terms. Okay, so from 1 to n, that's what you would plug in. This part right here, I'll change colors, is basically your function. What else do we know here? We know we're going to start at 1, we're going to stop at n. Okay, and basically you end up plugging in n equals 1, n equals 2, n equals 3, up to n. So you're going to have to stick with me here. We're going to try a couple examples, then we'll talk about some notation, how this relates to calculus. The notation gets a little tricky, so just, again, stay open-minded with me and see how this goes, and we'll kind of see how this connects. So first of all, take a look at 1 and 2 here. This is, again, review. So 1 squared, 2 squared, 3 squared, 4 squared. So if you had to come up with a function, what's happening? We are squaring a value. So we could say it's k squared. We started at k equals 1, and we ended at k equals 4. Not equals 4 up there, sorry, just do 4. So we go k equals 1 to 4. That would be this Riemann sum here in sigma notation. Okay, how about 5 plus root 2, 5 plus root 3, 5 plus root 4, etc. Okay, so there's a couple ways you could write this. You could say we start at 2 and go to 6. So that would be, so you'll notice it's 5 plus root, something. You could say x, you could say k, whatever it may be. And x starts at 2 and goes to 6. You also could say, oh, we start at 0. So if you said if x is equal to 0, how would I get 2? Well, that would have to be 5 plus root 2 plus x, or x plus 2. And we only go up to 4. So notice they could be written different ways. Again, that's just a quick review for you guys. And now we'll kind of see how this connects to LRAM, RRAM, all that fun stuff, and integrals. So as you can see in this picture, this is an LRAM. You'll see it intersects at those left-hand corners, okay, from A to B. And delta x is going to be equal here. So delta x is b minus a over n, as you know, hopefully. Your x values, if you were to go step by step, we're going to be at a, and then typically what we do, like let's say this was 1, and delta x was 1. Well, then we would do 1 plus 1, 1 plus 1 plus 1, 1 plus 1 plus 1, right? You would keep adding delta x onto it. Okay, so we're just going to say we add delta x, then we add 2 of delta x, then we add 3, etc., up to n delta x's. So the next x value would be a plus 1 delta x, a plus 2 delta x, a plus 3 delta x, etc. So I'll just put dot, 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 up to a plus n delta x. And this really represents b, right? That final value. So we don't know what it is. We don't know how many rectangles we have. So some n amount of rectangles. Again, stick with me here. I know this notation gets kind of tough. So if we were to do an LRAM, right, we would take delta x. Since it's equal, we can leave it on the outside. So delta x times all of the heights of the rectangles. The heights, you'll notice, would be f of a plus delta x, f of a plus 2 delta x, etc. So f of a plus delta x plus f of a plus 2 delta x plus, etc., and up to f of a plus n delta x. And again, this really means f of b. Okay. So what we want to think about here and how we're going to connect this to integrals is what happens, okay, to our approximation if n approaches infinity. And again, that's the number of subintervals, right? So what if we have infinitely many subintervals, right? I remember on that first day of notes, LRAM and RRAM, if we drew 2 rectangles for an approximation versus 8 versus 30 versus 60, if you drew in more and more rectangles, it's a more and more accurate answer. And the exact area is actually coming from the idea that if we approach infinity, or if we have infinitely many rectangles, we would find the exact area. So we know delta x is equal to b minus a over n, as we mentioned. So if I took n and brought it to infinity, okay, if I divide something by infinity, this is the same as 0. Okay, delta x would get extremely, extremely small. It would specifically, delta x, the width, would approach 0. Okay, so the subintervals get extremely small. So we have infinitely many rectangles. AKA the exact area. So that's good news because we know how to find the exact area. We're about to see this. It's an integral. We've already learned about it. So now we're just going to connect. Where did this come from? So again, what you want to think about, and this is a common theme in calculus, is as we bring n to infinity, okay, we draw closer and closer to 0. Okay, so for that limit, that's telling us that we have delta x is so tiny, we brought it all the way to 0, meaning we have infinitely many rectangles, meaning we have the exact area. Obviously, we're not going to sit there and calculate infinite rectangles. It's not something we can actually do. So take a look at the next part here. You'll kind of see, again, more notation. Don't panic. You'll see this is delta x right here. You see delta x again. So that's where this is coming from. Okay, so basically what happens here, and if we were to rewrite this, okay, this would be that, again, infinite sum from 1 to n. You would have the limit as n approaches infinity of delta x times all the heights, right? F of a, I'm sorry, this should be 0 here. F of a plus 1 delta x plus f of a plus 2 delta x, okay, plus dot 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 f of a plus n delta x. That same idea here. And again, this would find us the exact area if we could do it, but we can't. Excuse me. So since we can't do infinitely many, okay, we came up, well, not we, mathematicians came up with this great way of doing it, which is an integral, which we've seen. We know how to do this. And so that's exciting for us. We can actually rewrite these kind of crazy looking sums or complicated looking sums as an integral. Okay, so we already know a lot of these pieces here, but just to refresh your brain, this is kind of like a stretched out S. And what I want you to think of, this is the sum of infinite rectangles, S for sum. Dx, remember that's just telling you you're taking the integral with respect to x. And we have a and b. That's going to be the same thing we were doing with LRAM, RRAM, the start and finish. So that's not really a change there. And yeah, basically the nice part here is what you're going to do. You'll see on the next page, you're going to see some craziness. By craziness, I guess I just mean sigma notation, and sometimes these just get a little overwhelming. We're going to rewrite them as simpler looking integrals, okay, that mean the same thing. So we're going to be using this notation. We're going to have to kind of pick out pieces of what we saw in order to find the integral. So that's why we kind of needed this basis of how to get there. All right, so let's take a look then at number 1. We're going to try each of these, see how it goes. So we've got limit as n approaches infinity, and again, they're all a little bit different in terms of how they're written, but this is how we're going to find exact area without infinite rectangles. So it says for a to b, so that's good news, gives us a and b. Okay, whenever you see this like c sub k, that just means the variable, so we could just call that x. And we've got times delta x, and so what we've got for our function, right, this inside is kind of your function here. We've got the integral of x minus cosine of x dx from negative pi over 2 to 3 pi over 2. Again, infinitely many rectangles represents that same thing as our definite integral. That one's done. That's it. So take a look at the next one. We'll get a little more exciting here. Okay, so this first piece here, remember we mentioned this is delta x, okay? And on the inside here, this is really supposed to be a plus, and this would be basically b, but remember we called it n delta x. Okay, so that being said, it should be 4 over n, which is delta x, times n. Okay, basically think of it this way. If we plug in n here for k, all right, this would cancel, and you would have a, which is 0. So I hope you also notice that. A plus n delta x. We've got a is 0. You've got b would end up being 4, because this would simplify to n over n, which is 4. And then we also know this makes sense because we've got 4 over n right here. Delta x is b minus a over n, and we get 4 minus 0 over n, which is 4 over n, which is exactly what this says. So again, a couple ways to find b here. The easiest way, I think, finding it is taking this n value, plugging it in for k, all right, and seeing what that last term would be. So this term right here would simplify to 4, or 0 plus 4, because a is 0. So what do we got here, guys? 0 to 4, a to b. And our function, I know this is going to sound crazy, what's happening here is we are square rooting something. So square root of x dx. That's our final answer. So I know there's lots of k's, n's, everything like that, but once we kind of break this down, the overall function is a square root. Okay? All right, let's take a look at another one. I think this one's a little more clear. So very similar to number 2. Okay, you've got delta x is right here. So if you want to write that down, you know that b minus a over n is going to be 5 over n. So that's good to know. We have, in general, look at this function, guys. We have something being cubed. So you can have that written down. All right. This inside, again, says f of a plus I delta x. All right, so this would be a. Okay, so we've got 2. And again, how do we find b in this case? We could plug in n for k. All right, and then that last term would be 2 plus 5n over n, okay, which would give me 7. All right, so b, again, is that last term. So if I plug in the last number, aka n, we get 2 plus 5n over n, which is 7. So we would go from 2 to 7 dx. Okay, and that's our final answer here. How do we know this is right? You could also check it this way. 7 minus 2 over n is equal to 5 over n, so that's definitely the case as well. So that's good news. Okay, we're going to actually look at number 4 and 5 as well. 4, you'll notice it looks really similar, but now look, we've got each term written out. So that's going to be like as though it was an expanded format here. And if you take a look at 5, similar idea. So this is still delta x. Okay, so you could write that down. Delta x, which is b minus a over n, is going to be 3 over n. So that's just a good check, making sure that when you get a and b, they subtract to be 3. Okay, notice what's happening with your function. Cube root of something, cube root of something, cube root of something. So we've got cube root of x as our function. You've got a plus delta x, a plus 2 delta x. And you guys should be able to see this, right? If this is delta x, that would mean a plus 3 over n, a plus 2 times 3 over n, which would be 6 over n, a plus 3 times 3 over n, which is 9 over n. So this is making sense to us, hopefully. And last but not least, you've got a plus n delta x, okay, which is why these are going to end up canceling. And again, this last term, we wrote it up here. If you guys scan all the way back, that last term here really represented b, right? That last term, or where we're going to stop. So this whole thing, whatever this simplifies to right here inside, is going to be b. Okay, so we get 1 plus 3n over n, which is 1 plus 3, which is 4. Okay, so b is equal to 4. You'll notice in every single one of these scenarios, a was 1, a 1, a was 1. So we've got a is 1, b is 4. Does that make sense over here for our delta x? Is 4 minus 1 over n equal to 3 over n? Yes. So again, we're good to go. So I know this notation is a little bit crazy, a little bit complicated looking, but keep breaking it down, compare it to the general functions we used the general format we used on the first page, and see if we can get, again, we need the function, we need delta x, we want to just check that, but really we just need the function and then a to b. All right, so we're going to finish up with number 5 here. Okay, so take a look. Number 5, a little bit different thing going on. The main thing I hope you can see is we've got cosine, 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 cosine of something, so that is going to be our function. So that's good to know. Okay, then you've got, remember this would be a plus delta x inside. This would be a plus 2 delta x. This would be a plus 3 delta x. So we can kind of see delta x is this pi over n. Okay, pi over n. Then when you get here, you might also notice a is 0, because it was 0 plus pi over n, 0 plus 2 pi over n. Here would be 0 plus n pi over n. So b is going to be 0 plus n pi over n, which is just pi. So b is equal to pi. A is equal to 0. All right, great. We're making progress here. Seems like we're done. There's just this one little trick here, and I feel like this makes this problem an extra challenge. Take a look here. This is supposed to be delta x, right? But delta x is always b minus a over n, which in this case we got pi over 0, which is pi over n. And that lined up. We had 1 delta x, 2 delta x, 3 times pi over n, etc. So what you have to look out for here, and we're just going to finish up the problem with this little twist, this 2 right here is really that constant that would have been out front. So we have to recognize that. If it was 1 over pi over 3n, it would have been 1/3. So this 1/2 actually was a constant. It's just written inside of that parentheses. So I feel like it's a little bit hard to see. But again, you should be able to recognize this is 1 delta x was pi over n, 2 pi over n was 2 delta x. So we could see as we went that delta x was always pi over n. And we noticed it here as well. So that 1/2 has to go out front. It's not part of delta x. It is actually just a constant, which we've seen in front of our integrals before. So, little twist on that one. But besides that, guys, thank you so much for watching. And we'll obviously practice a little more in class. And let me know if you have any questions.